Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction and CC Bond Formation Application in Organic Synthesis. So, this course is by Professor Yashwant D. Vankar retired from Chemistry Department, IIT Kanpur, and my name is Sri Lakshmi. I am a PhD scholar in IIT Bombay. So today we have planned like we will be dividing the session into three parts. Like in the first part, we will have the discussion of some problems. In the second part, we will be having a discussion on the last week lecture contents. And in the last part, we will just summarize what we have been discussing in this session. So let me see who all are there. So I hope you have seen the week one lecture contents. So before going into the lecture discussion, we will be having a discussion about the week zero assignment questions. Have you all go through that? It would be better if you can unmute yourself and respond. Any of you? Okay. So at first we will discuss this week zero assignment questions. So the first question was paracids such as paracetic acid or metachloroperbenzoic acid readily epoxidize an isolated olefin like cyclohexene, but they do not epoxidize an alpha beta unsaturated ketone. So four options are given here. So out of this four options, which is the correct reason for this statement given here? So the first option is an isolated olefin is electron rich and paracid is electron deficient. The paracid is electron rich and thus it reacts with isolated olefins. An alpha beta unsaturated ketone is electron rich and cannot react with electron rich paracid. The paracid is electron rich and the alpha beta unsaturated ketone is electron deficient. Uh, do you know which is the correct answer? Why this metachloroperbenzoic acids or parasitic acids can easily isolate a isolated olefin, but they do not readily epoxidize an alpha beta unsaturated ketone? Why is it so? So basically, this is an interactive session, so it would be very useful for both of us if you could interact. Okay, so as we know, comparing an isolated olefin and alpha beta unsaturated olefin, an isolated olefin will be more electron rich as compared to unsaturated olefin because if we consider an alpha beta unsaturated ketone, the electron withdrawing effect of that carbonyl group makes the electron density less available in the olefin part. So that makes it less electron rich as compared to an isolated olefin. So out of these four options, the first statement which is correct is an isolated olefin is electron rich. And similarly, if we consider paracids like metachloroperbenzoic acid or any acids, there is electron withdrawing ester group on the both sides of this, or electron withdrawing carbonyl group on both sides of that peroxy bond. So that makes that peroxy acids or that peroxide bond electron deficient. So that's the reason it can readily isolate this mcpba or parasitic acid can readily isolate readily epoxidize an isolated olefin because it is electron rich, and this paracid is electron deficient. But they cannot epoxidize, or they do not readily epoxidize an alpha beta unsaturated ketone. We have to use certain other reagents other than paracids to epoxidize alpha beta unsaturated ketones. So the correct option here is option 1. If you have any doubt in between, please feel free to ask. Now the next question. So first question was about the epoxidation of isolated olefin. So the second question is about the epoxidation of alpha beta unsaturated ketone. So which reagent or reagent combination can be used to carry out epoxidation of an alpha beta unsaturated ketone? So the first option is metachloroperbenzoic acid along with the Lewis acid. Second one is hydrogen peroxide alone. Third option, hydrogen peroxide and a Lewis acid. And last option, hydrogen peroxide and sodium hydroxide. So, which combination of the reagent can be carried out to epoxidize an alpha beta unsaturated ketone? We already told that paracids or metachloroperbenzoic acid, paracetic acids, or any paracids basically alone cannot epoxidize an alpha beta unsaturated ketone. So, which will be the correct choice? So here the correct answer is, usually for the epoxidation of an alpha beta unsaturated ketone, we use the combination of hydrogen peroxide and sodium hydroxide. The correct answer is option 4. And what's happening here is, so basically this is H2O2. So the hydroxide ion from the sodium hydroxide will abstract proton of this H2O2, eliminating water molecule and form this O minus anion. And then this O minus will attack over this alpha beta unsaturated ketone at this fourth position, and then this double bond will shift over here, and this will shift over this oxygen. So here it will become O minus. Then again, when this O minus will come back, this will go and attack over this oxygen, and this OH minus will leave to form this epoxide. So this H2O2 and sodium hydroxide can give this epoxidation of this alpha beta unsaturated ketone, and the sodium hydroxide is used to abstract this proton from this H2O2, resulting in this O minus ion, this peroxy anion, we can say. Is it clear? Moving to the next question, what is the major product that will form in the following reaction? So we have benzoic acid. We are treating it with lithium in liquid ammonia using ethanol and water, and then followed by hydrolysis. So four options are given here, and we all know this is a named reaction also. So out of these four options, which would be the correct answer if benzoic acid is treated under this condition? So this is basically an example for Birch reduction. So the basic mechanism of Birch reduction is given here. So we are using lithium in liquid ammonia or sodium in liquid ammonia mostly. So that sodium in the presence of this ammonia will give this sodium ion and this electron will be forming. So that electron whichever is released will attack over that benzene ring to form this benzene radical anion. So this is attacking over here, this bond will shift over here and resulting in this radical at one position and anion at another position, that is known as benzene radical anion. Then what is happening, the protonation will take place. So that is why we are using ethanol or methanol or any proton source is required basically, so that this protonation of this benzene radical anion will take place. So this negative charge will abstract the proton from the alcohol and form this one, this compound, this radical. Then what is happening? Reduction of the radical to an anion by an electron. So another radical will add upon here and it will form an electron, and then again this will abstract one proton from that proton source, which is alcohol basically, and form this compound, cyclohexadiene type of compound. So it is basically what is happening, de-aromatization of benzene ring is happening, and we are starting with benzene and we are getting the cyclohexadiene. So this is a basic mechanism for Birch reduction. But when we have substituents over the benzene ring, where will be the radical formation taking place, or where will be the proton, new proton will be coming, proton abstraction will be taking place to which position, that depends on the substituent present in the aromatic ring. So depends on whether the substituent is electron withdrawing or the substituent is electron donating in nature. So that will control the position of the double bond in the product. So as we can see here, in this case, we are using benzoic acid. So this carboxylic acid is an electron withdrawing group. And so what will happen is this radical anion which will be formed in the intermediate step will be stabilized by this carboxyl group. So this radical anion over this anion at this position will be stabilized, and we will be getting this resonance structure where this negative charge is present in this oxygen atom. So that is a more stabilized structure compared to the other resonance structure possible here. So that is the effect of electron withdrawing groups. These electron withdrawing groups can stabilize the negative charge via resonance. That negative charge can be delocalized to that electron withdrawing group. On the other hand, if electron donating groups are present, the product is determined by electronic repulsion. So, electron, what will happen if this at this position, this negative charge is here? So, here an electron repulsion will be there because already an electron donating group is present at this position. So, that will also push electrons to, and already the negative charge is present at the center. So, that there will be an electron repulsion. So, this structure will, or this form will not be preferred, and what will happen, this shift over here and negative charge will come over this center, and here then protonation taking place. So in the case of electron donating groups, this ipso protonation is not preferred. This kind of products will be observed. Then again here protonation will happen, and the same mechanism which we discussed before will follow. Again electron donation, and here in the place of radical anion will be generated, then again proton abstraction, and we will get the product. So if electron donating groups are there, this kind of products will be formed. And if electron withdrawing groups are present, this kind of products will be formed. So here the correct answer of this question would be option C, because benzoic acid is used and this ester group is an electron withdrawing group. So that is the basic mechanism of Birch reduction, and how the substituent present in the aromatic ring controls the position of the double bond, controls the where the proton abstraction will happen, and where we will be getting the double bonds. So substituent effect on the Birch reduction. I hope it's clear. Moving to the next question, when the following optically active molecule A is hydrogenated in the presence of palladium carbon catalyst, the product B is formed. The conformation of the product is, so here we have this compound A, which is already having this double bond, which is substituted with methyl group and phenyl ring, and we have this aldehyde, which is below the plate. So in under hydrogenation condition mediated by this palladium and carbon, this double bond is getting reduced, so the product is also given here. So we have to identify the correct conformation of the product. So what will be the position of methyl group, phenyl ring, and where will be the incoming hydrogens coming, so that we have to see from the four options we have to correctly analyze which conformation will be preferred, or which will be the conformation of the product obtained here. Can any of you try this one? Kushal, Jadin, Sanjoy, I am seeing three of you. Can any of you respond? A. Okay, can you explain that? You can unmute and answer.
Hello.
Yes.
In presence of hydrogen palladium,
Yeah.
here cis product is formed.
Cis product is formed means with respect to what you are telling.
Therefore, we study option A, B, C, D,
Yeah.
cyclohexane compound. This is the chair form,
Yeah.
where the cis product is prominent.
Yeah.
We see we see in case of A,
Mm.
in case of A, two hydrogen uh, up below. Oh no sir, up the plane, below the plane.
Yeah. In
अच्छा,
option, this are the two
eh,
hydrogens which are incoming. These are
up
cis, right?
है है up below,
Yeah.
or therefore most probably the B will be the correct answer. মানে up below, মানে two hydrogen will be the same space,
Yes. Yes.
maybe up or below,
Yeah.
মানে I can say this. মানে in presence of hydrogen palladium cis hydrogenation will occur.
Yes.
তাহলে when we study among four option A, B, C, D,
Mm.
uh, when we draw, two hydrogen will be the same space,
Yes.
maybe up or maybe below.
Yes.
Yes.
So, and one more thing you can consider here is the presence of this aldehyde.
Uh, Aldehyde.
Yes.
Aldehyde is below the plane,
Yeah.
therefore up and below. Two condition will be considered.
Yeah.
Aldehyde is below the plane,
Yeah.
and hydrogenation occur in the same space, maybe up, maybe below.
So, which will be preferred? If aldehyde is below the plane, the incoming
Uh,
hydrogens will prefer above or below position.
Incoming hydrogen will most probably above the plane.
Yeah. So, which will be the answer then?
Then must be a answer. CH is below the plane. Okay, B will be the answer.
Yes. B
B.
is the correct
B.
answer. Yeah.
B is the answer.
Yes.
Actually, here clue point is CHO is the below the plane, and hydrogenation occur in cis fashion.
Yeah.
As CHO is below the plane, incoming hydrogen will মানে endo phase, endo, this is endo space, that is above the plane.
Yeah. So,
Okay.
the 2 points you have to consider here, that for hydrogenation condition, always the both of the hydrogens will be coming cis fashion only. It will never be opposite. And another one is the controlling factor, which is the aldehyde stereochemistry.
ম্যাম থ্যাংক ইউ মানে ওয়েল ক্লিয়ার।
Yeah. Moving on to the next question, the major product that will form in the following reaction. So here we have this alpha beta unsaturated ketone, and we are treating it with two equivalents of methyl lithium and one equivalent of copper iodide. So which will be the correct answer here?
Most probably C will be the correct answer.
C, can you explain how?
Because it is the Gilman rearrangement.
Yes.
Gilman,
Yes.
that is 1,4 addition will occur.
Yeah.
Okay, 1,4 addition here only option is uh, uh, C and B. C and B.
Yes.
Okay,
Yeah.
and then iodine will attack the below the face.
But here we are not using any proper iodine source, right? This copper iodide we are using for the formation of Gilman reagent. So what is Gilman reagent?
Me2CuLi.
Yeah,
Yeah.
organocuprine. So if we are using
Uh,
two equivalents of methyl lithium and one equivalent of copper iodide, that is completely used in the formation of Gilman reagent. And that iodide mostly don't react like that. Like we have,
that is B will
yeah, B will be the correct answer. Only Gilman reaction is happening here.
role of iodine only Gilman formation of Gilman reagent it will occur 1,2 addition product.
1,4 addition product. So option B will be the correct answer. Now the next question, the major product that will form in the following reaction. So here we are using phenyl acetic acid and we are treating it with diazomethane. So which will be the correct answer here?
Most probably B will be the correct answer.
Yes, B will be the correct
B.
answer. So what is happening here is, firstly,
Dilation occur.
yeah, this proton will be taken by the CH2 of this diazomethane and that will form this carboxylate anion, and then this O minus will take the CH3 and nitrogen will leave. So that will be, usually for the esterification of acids we can use this diazomethane. So the correct answer is option B. Now the next question, the major product that will form in the following reaction. So here this cyclohexene derivative is there substituted with the methyl group. We are treating it with dimethyl sulfide, dimethyl sulfide complex. In the second step, H2O2 and NaOH. In the third step, chromium trioxide in presence of an acid. And in the fourth step, methyl vitic with sodium hydride. So four reactions are, or four or three reactions are happening here.
Most probably A will be the correct answer.
A.
I may I explain
Yes,
this?
yes, sure.
Actually, first and second step is the hydroboration reaction.
Yes,
Uh, it will undergo OH will occur as the less sterically hindered position.
yes. So you
Uh,
are telling,
and then in third compound is CrO2, it will undergo the oxidation
yeah,
and then Utic reaction and then Utic reaction.
yes,
That is most probably A will be the correct answer.
yes, you are correct. So first step is hydroboration. So hydroboration and then followed by oxidation will give hydroxyl group at this position. That hydroxyl group will be oxidized into ketone by this chromium trioxide in acidic medium, and then methyl vitic will give this olefination. So this is the mechanism, or this is a brief summary of hydroboration, what is happening. So we are using BH3 dimethyl sulfide complex, so that will add upon this double bond in a syn addition fashion, and we will be getting this organoboranes. Then in the presence of H2O2 and NaOH, this BH2 will be replaced with this hydroxyl group. So always remember that carbon oxygen bond, or that hydroxyl group will be formed on the least substituted carbon. This boron will be always attacking on the least substituted carbon, and on the same position only this hydroxyl group will be forming. So first step is this hydroxylation of this double bond. Here OH will come, then that OH oxidation to a ketone using chromium trioxide, then methyl butyl olefination. In the presence of NaH base, we will be getting this option A. Now, this last question of this week zero assignment. The absolute configurations at the asymmetric centers labeled A and B in the molecule, whose Fisher projection is as follows. So you have to assign the stereochemistry for this A center and this B center.
A will be the most probably correct answer.
Yeah, can you explain?
Actually, hydroxyl is the more priority group. It will numbering one.
So
Eh?
which one you are still telling, B or A?
B B B B B
Okay.
B B
Yeah,
B.
so this
We
will
when we consider chiral atom B,
okay.
OH is the most priority group.
Yes.
Therefore, it will numbering one,
Yeah.
and then go through CH2OH
Yes.
will be two. Can in, and then the lower group it will be the three, and hydrogen will be the D. It is
Uh,
clock.
you're sure?
Hello.
Because here one bromine is here, so which will be,
Oh, then sorry, ma'am. In the lower part will be the B.
yeah, so
Okay.
this will be 2 and this will be
And
3.
this will be three, and this will be four.
Huh.
That is one. Just
1,
a
2,
minute.
3 will
Just
be
a
which
minute.
fashion it is? Anti-clockwise, right?
One, that is one, two, three. That is anti-clockwise.
Yeah,
That is clockwise. Yes, it will be R,
yeah.
R,
So B is
R,
R, yeah.
R. A
And
is
A
R.
is,
A is here. BR is one,
yeah,
one, and then go through COOH group.
yeah. So this
C
will be 2
two,
and this,
and it will be three, and it will be four. That is one, two, three clockwise.
yeah,
Clockwise R, it will be S.
S,
That is RS. B
yeah,
will be the correct answer.
yes. This will be the correct answer, right? Option A, because this is S and this is R.
And they are A will be the
A
correct
will
answer.
be the correct answer. So these are the questions in week zero assignment. So I have kept only this for today. If you have any questions regarding the lecture one contents of, or if you need any additional information about any reactions, you can ask.
Ma'am, I asked a question. I cannot join your lecture in the at the beginning.
Okay.
This video lecture will be available after
Yes, yes. This video lecture and
finishing.
this slides will be shared with you by the NPTEL team. You will get the
Share
link
with you,
to
mane
the video.
oxidation reaction NPTEL courses. It will be available.
Yes, yes. In that portal only, it will be available, and that link will be separately shared to you.
Ma'am, am I asked another question
Yes.
regarding mane theory exam purpose?
Yeah.
If you kindly add any reference book or supplementary notes or question answer, then we'll be highly grateful and enriched.
Yeah.
If you
Like
pro.
which topics you need? This topic only or any other
Now
topic?
entire the whole this courses.
I think in that
Any addition?
NPTEL platform itself, we have this lecture notes available.
Okay, okay, okay.
Yeah, you can just go
Okay,
through that.
thank you.
If you are not able to find it, let me know. I will share with you.
Okay, thank you.
So if you have any further question regarding the week 1 lecture contents, you can ask, because it is the first session, so I have kept just this 8 questions only for today. Okay, then we will just have a brief discussion about the last week's lecture contents. I'm not going to discuss anything in detail. If you have any doubts or anything in between, you can ask. So, in the first lecture, we have seen this introduction to organic synthesis, importance of selectivity, basics of oxidations, and how the sulfur based oxidations was developed. And we know in organic synthesis, we will be having a target molecule. So, that target molecule can be a natural product or any other non natural product which is of interest, that is, which can be of biological interest, material interest, or from any other angle. So, there will be some target molecule. So, in each of the organic synthesis procedure, we will be having some steps to reach this target molecule, and these steps we will call as synthetic methods. And for achieving each of these steps, we will be using certain reactions and certain reagents. So, this includes oxidation, reduction, carbon carbon bond forming reactions. So this course mainly focus on the mechanisms of the reaction, selectivity of the reaction, how particular stereochemistry is preferred over another one, and how these reactions or how certain reagents are applied in the synthesis of natural products, or generally we can say how it is useful for organic synthesis. Then we have seen several examples for natural products which involves alkaloids, terpenes, steroids, and then we have seen water terpenes, which are basically compounds consisting of isoprene units, and water terpenoids. Terpenoids are secondary metabolites which are derived from terpenes, but it is having multiple cyclic groups and oxygen. Then we have seen certain examples for terpenes like geraniol, carvone, camphor, and for terpenoids, this taxol is an example for terpenoid. Then artemisinin is another example for terpenoids, and this taxol is an anti-cancer molecule. So then we have also seen how this taxol synthesis is achieved. Like commercially, this taxol is produced by a semi-synthetic route because its isolation from natural sources gives only very small amount. So the total synthesis is not a practical approach for the formation or for the synthesis of this taxol. So this semi-synthetic route is preferred. So in semi-synthetic route, what they are doing is another compound is there which is closely related to taxol, that is 10-deacetyl-baccatin, which can be isolated from the trees in bulk quantities. But this taxol cannot be isolated from the trees in bulk quantities, but this 10-acetyl-baccatin can be easily isolated from the trees in bulk quantities. So people are isolating that from the trees, and then they are using that for converting it into taxol. So it in like in few transformations, this 10-acetyl-baccatin can be converted into taxol. So that type of methods are known as semi-synthetic methods. Then we have seen this examples for alkaloids, which in alkaloids are basically naturally occurring organic nitrogen containing bases, and some examples are morphine, nicotine, strychnine, and papaver. Then we have also seen examples for steroids. Steroids are basically man-made version of chemicals which are also known as hormones, which are present naturally in human body. And the examples involve estradiol, cholesterol, testosterone, progesterone. Then we have seen this prostaglandin. So prostaglandins, as given here, is physiologically active lipid compounds, and they are also known as eicosanoids, and they also exhibit diverse hormone-like effects. Then there are enzyme inhibitors. So enzyme inhibitors basically inhibit the action of certain undesired enzymes. An example is Tamiflu. Then this insect pheromones, and pheromones are basically this sex hormones in insects. So examples for that involves this dibutyroxynorine. And then we have is basically an organic synthesis. Like there will be several steps, like we have the starting material A, which we convert into B, then C and D, and then finally after several steps we are getting this target molecule. So for each of this transformation we will be using a certain reagent or combination of reagent for carrying out each of the specific reactions. And then we have seen this example for this Diels-Alder reaction, as well as this benzylic oxidation, then functionalization of this alpha position, then this double bond formation, then reduction. So all this we know, these are some set of reactions, and some combination of reagents can only give this certain specific reactions. So that was the then we have seen about development of synthetic methods, like different reagents, reactions, and what are synthons. Then how selectivity will be different, like different types of selectivity. For certain reaction we will say chemoselectivity. Like in this case we will say chemoselectivity because this ketone and this ketone is different, because this is an isolated ketone and this is alpha beta unsaturated ketone. So that case we used to say chemoselectivity. Then regioselectivity, basically for the position of like if we want to do alpha substitution or alpha functionalization of this ketone, two positions are available, this position also and this position also. So there we use this term regioselectivity. Then another term is this stereoselectivity, where we use this enantioselectivity or formation of enantiomers, or diastereoselectivity, or we say formation of diastereomers. So, can anyone of you tell what is the main difference between what is the difference between enantiomers and diastereomers? What are enantiomers and what are diastereomers?
Yes, ma'am. Yes, ma'am.
Yeah.
Am I explained?
Yes. Yes. Sure.
Enantiomer means non-superimposable mirror image is called enantiomer.
Yes.
Having having stereochemistry, non-superimposable mirror image.
Yeah.
Okay, ma'am. Diastereomers, there is no mirror image relationship.
Yes. So
মানে
here, if you see this four compounds, can you tell the relation between one and two?
They are mirror images of each
one
other,
Yes.
ma'am.
So they will.
one and two are and
Hello.
one and two are mirror image to each other.
Yes. So they will
Non
be
not,
enantiomers,
not
right?
enantiomer, non-superimposable mirror image, that is it is enantiomer.
Yes. And three and four also enantiomers, right?
Is all both are enantiomer.
Yeah. So now if you see the relation between this 1 and 3,
Diastereomer.
yes. So here as we can see, one chiral center is fixed in both of the compounds. Only the other one stereochemistry is changed. So they are not superimposable and we call them diastereomers. So clear, right? The difference between enantiomers and diastereomers.
Okay, okay, clear, ma'am.
So then the same case we have seen for this hydrogenation also. So as we said in this problem solving session, hydrogenation will be always taking place from the same phase. So both the hydrogens will be coming from the one phase only in the cis fashion. So either it can be above or it can be below. So here also these two are related as mirror image. So these are enantiomers. Similarly, these two are enantiomers, but this are diastereomers, and this, if we cross it, all are diastereomers to each other. Then in
Am I asked one
yeah, yeah,
question?
sure, sure.
Eh, eh,
Hello.
Hello.
Yeah,
In question answer discussing session, you said that as CHO is the below the plane,
yeah,
when hydrogen palladium hydrogenation occurs, in case of cyclohexane type compound,
yeah.
hydrogenation always, hydrogen attack in the above the phase. If
Not
you
always. Like if there is no particular functional groups controlling the stereochemistry of that hydrogenation, it can come from any phase. Like it will be always cis, but
okay,
either both of them can come from above or both of them can be coming from below. Okay, that's why here they have given four answers. So here all we,
Oh,
here both the hydrogens are above, here also both are above, here both are below, here both are below. So this four possibilities are there because there is no other controlling factors, no chiral centers, nothing is there.
but here CH2 is below the plane. Here here CH was the controlling factor. When question answer discussion, when you explain one hydrogen palladium hydrogenation occurs, CH2 is below the plane. Here hydrogenation occurs above the plane, but here is no determining factor.
No
I
determining
just please
factor.
clear this.
Yeah, so here all are
Okay,
possible, either
okay,
below or above, both are possible, both are equally favorable.
okay, thank you.
Yeah. Then we have seen this chromium, just an introduction to this chromium trioxide mediated oxidation and how this mechanism is going. So I am not going into the detail. If you have any doubts, you can ask. Just I will quickly go through this. So here that yeah. So one discussion was about whether this proton abstraction will take place from this intermediate, like directly this oxygen will take this proton, or first base will take this proton and then like it will go through this 5-member transition state or this 5-member transition state in an intramolecular fashion or intermolecular fashion. So that was the discussion. So for discussing that, we considered the sulfur based oxidation, and we have seen several examples for sulfur based oxidation. And this first one, we started with swan oxidation, but before swan oxidation itself, we have seen the discussion about this Moffat Fitzner oxidation and this Barton oxidation. So in Moffat Fitzner oxidation, basically we are using the combination of DMSO with this DCC in presence of catalytic amount of H3PO4, and Barton had used this force gene in place of DCC along with this DMSO. So this is the basic mechanism for almost all the sulfur based oxidations are having similar kind of mechanism. So in the first step, what will happen is this DMSO. So this O minus will attack over this carbon of this DCC. So this is DCC, dicyclohexyl carbodiimide. And then this nitrogen lone pair will take the proton from this H3PO4. Somebody have asked a question. Actually, I don't have any access to do that. Maybe you can inform the NPTEL team, and if they can arrange that, it would be helpful because I just have this TA responsibility only. I don't know who all are the participants also. So if they can do that, it will be better, and I will be happy to join. Yeah. So that will give rise to this particular intermediate. Then what is happening? We have our alcohol, which is our reactant. So that alcohol oxygen lone pair will attack over the sulfur, and this will be the leaving group. Again, this will leave, and this nitrogen will take another proton from this H3PO4. So that will give rise to this particular intermediate. So this is the basic intermediate for almost all the oxidation reactions involving sulfur. Then what is happening? This dimethyl sulfide will eliminate. So from, if we consider so here what is happening, either this proton abstraction can take place from this CH3 resulting in the formation of this ketone, or directly what can happen, this proton abstraction, if there is like one proton here, that proton can go here and this can break, eliminating this dimethyl sulfide and forming this ketone or aldehyde, whatever it is. So here one of the major drawback of this Moffat Fitzner oxidation is the formation of this dicyclohexyl urea. So this is the byproduct of this oxidation, and it is very difficult to remove this dicyclohexyl urea doing column chromatography. It is very difficult to remove this. So that's why this DCC DMSO combination is not generally preferred nowadays due to the purification issues. So this intermediate you have to keep in mind for all the most of the sulfur mediated oxidation reaction. This type of intermediate will be the common one. So as I said, this dicyclohexylurea is difficult to remove from the product, and that is why this is not commonly used. Then another similar oxidation is Kornblum oxidation. There we are using the combination of DMSO and a base, which can be sodium bicarbonate or K2CO3. Again, the same mechanism is happening here. Like first, O minus from the DMSO will attack over the CH2, Br minus is leaving and forming this intermediate. Then base is taking this proton, and that is DMS is leaving, giving rise to this oxidized product. So here we are Kornblum oxidation, as we can see, we are using this halogen substituted compound, and that we are converting directly into aldehyde. This is not going through alcoholic stage. Any living group can be used. Like here OTS is used, here Br is used. So anything can give this oxidized product. So that is Kornblum oxidation. Then Kornblum, Barton, Moffat, Pfitzner oxidation, Torsel, they all studied this, where this mechanism happens through intermolecular fashion or intramolecular fashion. And another oxidation is this Parik-Doring oxidation. They are also similar. Along with DMSO, they are using this pyridine SO3 complex. And then there is Korekim oxidation, and later comes this Swan oxidation. So as we can see, all this are basically doing the role of electrophiles. DCC, this phosgene, COCl2, pyridine SO3, and in place of that, people have used acetic anhydride, trifluoroacetic anhydride, trifluoromethane sulfonyl anhydride. All these are basically modification of the same oxidation. Then we have in the lecture 3, basically we have seen this Korekim oxidation, this combination of dimethyl sulfide bromine, then this NCS combination. So here, like dimethyl sulfide in the presence of this NCS can give this compound. So that again, this N minus will attack over the sulfur, Cl will leave and this intermediate will form. So for this Korekim oxidation, this is the reactive intermediate. Then the same mechanism, this oxygen lone pair will attack over the sulfur, forming this intermediate. Then same way we will be getting the oxidized product. So that is Korekim oxidation. We are using an additional halogen source here. Now comes the Swan oxidation. So for Swan oxidation, we are using the combination of DMSO, oxalyl chloride, and triethylamine. So oxalyl chloride, one of the advantages is that it is high boiling, and all the byproducts formed in the reaction are water soluble. So workup will remove mostly all the impurities or whatever byproducts formed. And one of the necessity of this reaction is this reaction should be done at lower temperature, minus 68 or minus 60 degrees Celsius is necessary for the formation of that key intermediate in this reaction. So that is one of the crucial point of this reaction. So this is the mechanism of Swan oxidation. So this is DMSO and this is oxalyl chloride. So this O minus will attack over this carbonyl carbon, and the Cl minus will leave to form this intermediate. Then again what is happening, the Cl minus will attack over the sulfur, and this act as the leaving group now, and this will leave to form this intermediate. So this is the reactive intermediate in this Swan oxidation. Then again, as we discussed earlier, the same mechanism, oxygen lone pairs will attack over here, and the Cl minus will leave to form this intermediate. Then here, as we can see in the mechanism they have given, triethylamine is not directly taking this proton, but it is taking the proton from the methyl group attached to the sulfur. So that will form the CH2 minus. Then that CH2 minus is taking proton from here, and this is coming over here, DMS is leaving, and we are getting this aldehyde. So this is the crucial part of this mechanism, like whether to decide whether this proton abstraction takes place intramolecularly or intermolecularly. So first proton abstraction by the triethylamine is taking place not from here, it is taking place from this CH3 of this sulfur. And then that CH2 minus is taking the proton attached to this carbon, which is attached to the oxygen. So this proton abstraction is basically taking place in an intramolecular fashion and not intermolecular fashion. That means no external source is abstracting this proton. The CH2 minus present in the same molecule is abstracting this proton, resulting in the formation of this product. And another thing we have seen is how the temperature can affect this reaction. If temperature is not maintained properly, some side reactions may occur, and this Pumara rearrangement type of reaction can take place. So what will happen, as we have seen, this intermediate will be formed, and if temperature is not negative, temperature is not lower, then Cl minus will take proton of this CH3 and it will form this intermediate. Then again Cl minus will attack over this carbon and this will give rise to this product. So that will give, finally we will be getting this undesired product rather than our desired oxidized product. So that is why this temperature maintaining is very crucial in Swan oxidation. So this is the basic Pumara rearrangement. So here what is happening? Pumara rearrangement mechanism is like that. So this can exist in this form also. Then treating with acetic anhydride, this oxygen, like here acetate formation is taking place. Then what will happen? Proton abstraction from this position by this acetate ion will result in this intermediate. Then again OAC minus will attack over here and this double bond will shift over here, stabilizing the positive charge, and we will be getting this intermediate. So this is the product we get in Pumara rearrangement. So this is not exactly Pumara rearrangement. A modified Pumara type of rearrangement will happen if temperature is not maintained in Swan oxidation. Then we have seen in the fourth lecture, we have seen several examples for seleno-pumara rearrangement. So similar to sulfur, selenium also reacts in a similar fashion. So with acetic anhydride, as we seen just before, here OAC will be coming. Then what can happen? If we treat this selenium compounds with 30% H2O2, it will be converted into MCPB, or H2O2 can convert selenium into selenoxide. So Sc double bond O will be there. Then if we heat it, usually this elimination can take place. So here elimination is taking place from here, this is coming here and this is getting removed, so this alkene formation can take place. So this is an example for seleno-pumara rearrangement. Same here also, first this pumara rearrangement, MCPB acetic anhydride reaction will give this OAC installed at this position. Then in H2O2 pyridine condition, either proton abstraction can take place from here or from here. But considering the steric factor, proton abstraction will be taking place from this position and elimination will take place to give this compound. So that is an example for seleno-pumara rearrangement. Then we have seen how this epoxides react with this sulfur reagents. So here, as we can see, if we are treating this particular epoxide with this dimethyl sulfide bromine complex, so here first this oxygen will coordinate with this, or this, yeah, oxygen will coordinate with the sulfur, attack on the sulfur and form this intermediate, and then Br minus will attack over this carbon, epoxide will open to form this compound. Then again the same mechanism can happen and we will be getting this alpha haloketones from epoxides. So this is one of the synthetic utility of this sulfur type of oxidation. Directly epoxides can be converted into alpha haloketones. Then another example is this combination of this DMSO and BF3 etherate will give this alpha hydroxy ketones. So how that is happening? First, this BF3 etherate is a Lewis acid. So it can coordinate with this epoxide oxygen, giving rise to this compound. Then DMSO O minus will open this epoxide. This will form. Then similar to that of whatever we have seen in Swan oxidation condition, we will be getting this alpha hydroxy ketone. Then here we have seen this oxidative decarboxylation of carboxylic acid to carbonyl compound. So here what is happening? First LDA or N-butyl lithium will abstract proton from this center, and treating with this reagent will install this methyl sulfide at this center. Then N-chlorosuccinimide in presence of methanol or ethanol do chlorination of this sulfur and give this intermediate. Then what can happen is this decarboxylation takes place. So this O minus will come over here, this will come over here, and the Cl minus will leave to form this compound. Then this upon hydrolysis can give this ketone. So here we can see we have started with this carboxylic acid and we are getting this ketone with one carbon less. So that is another synthetic utility of this sulfur mediated reactions. Then, as I have told earlier, the sulfoxides or selenoxides with a beta hydrogen atom can readily undergo syn elimination on heating. So, the one condition is that hydrogen should be available, and this hydrogen and this sulfur or the selenium should be in syn fashion to undergo elimination, cis fashion to undergo elimination, and we will be getting alkanes here under heating condition. So, we have seen several examples for that as well. Um, yeah, so that was basically, then we have just seen an introduction to SeO2 mediated oxidation also in the last lecture. So yeah, if you have any doubts or any question regarding any of this topic, you can ask.
Ma'am, I asked a question.
Yeah.
Ma'am, you nicely explain all type of oxidation, that is swan oxidation, chrome bomb oxidation, and so many oxidation basically based on sulfur based,
Yes.
and go through intramolecular hydrogen pressure, and S positive ion is formed. When we go through the mechanism, please sum up, the point, highlight the point how we will remember very easily. Please
Like,
sum.
it is difficult to remember all the name of the reaction, right? Like which
Okay, ma'am.
reagents. It is difficult. I understand that. Like if we see some reagent combination, it will be difficult. Okay, this is one oxidation. This is Moffat-Sitzner oxidation. That is difficult to remember. But we can predict the mechanism, right? If we see the combination of reagents, we can always predict the mechanism. Like
Okay.
if we see here DMSO BF3 use, first thing should come to our mind is DMSO. Okay, DMSO can attack over that carbon. Or a BF3 is a Lewis acid, it can coordinate with the oxygen. So this mechanism we can predict always. So always
Okay, ma'am. Okay.
better to uh, try ourselves the mechanism rather than mugging up all the name reactions. It is difficult. We cannot remember all the name reaction because that many name reactions are there. It is very difficult to remember names of each reaction. But at least if we see certain reagent, okay, this I have seen somewhere, this should go through this, like that. If we think by the mechanisms, it would be more easier.
Okay,
Yeah.
ma'am. Okay.
Any other questions? Okay, if not, we will conclude today's session here. Hope you all enjoyed.
Ma'am, which book should we follow for this paper?
I will share with you in next class. Is that okay? I will make a list of all the reference books you can follow, and I will share with you in the next class.
Ma'am,
Okay, ma'am.
your total entire lecture today, entire lecture is available in NPTEL site.
You're asking about this video?
Not this today whole session, that is 1 hour and 1.5 hour. The total session is available in NP. Again, where I repeated your lecture.
Yeah, yeah. You
I
will
mean
get
the.
that. This everything will be uploaded in that NPTEL portal. You can access that anytime.
Okay.
All this tutorial sessions and all the slides, whichever I am showing here, everything will be available for you.
Sanjay Babu, are you Bengali?
No.
আমি বাঙালি. My number is
Oh,
9932181838. Ma'am, just a minute.
Yeah, yeah, sure, sure.
99.
32
Oh,
18
one
18
18
18
18
38
1818.
38.
Oh, 181838, তাই তো?
হ্যাঁ, আপনি কোথায় কি করেন?
আপনার কোন কলেজ স্যার?
So what
আমার
you guys are
খড়গপুর
doing? You
কলেজ।
guys are PhD
ও আচ্ছা,
students or
ঠিক আছে।
what you guys are doing?
Actually, ma'am, I already completed my PhD,
Okay.
and now I go through postdoctoral, and NPTEL course is very essential.
Yeah.
I already 3 times stop all. Okay, okay, okay. Thank you, ma'am.
Yeah, yeah, yeah. Thank you.
Thank you.
Okay, if there are no other questions, you can leave. We'll see you in the next session, which will be on next Saturday.
Ma'am, the assignments when we have to submit it?
I think within a week of like each assignment, you have to submit within a week maximum.
One week.
Yeah, 1 week or maximum 1.5 weeks they are giving, I think.
So it is the first lecture of our team. No?
Sorry.
It is the first lecture of this
Yeah, this is
oxidation
the first
group.
tutorial session for this NPTEL course. So we will be having
Oh,
around 12-week lectures. So 12 tutorial sessions will be there.
this is first one, no?
This is first one. And if you cannot, in case if you cannot join in any of the session, all this video recordings and slides will be available for you in the NPTEL portal.
Oh, and first assignment is given there, ma'am.
Yeah, yeah. First assignment is already there. You can try that.
Oh, just after clicking, it will be active, no?
Yes, yes. Just go to week one content, and in below that week one contents, week one assignment will be there.
But in my mail there is no assignment, first assignment. For that I am asking you.
Just go to that NPTEL portal once and see directly.
Oh,
Yeah.
it will not be obtained from our mail ID, no?
Usually it used to come, but I don't know whether it came or not this time. Usually it used to come in mail.
Oh,
Yeah.
okay, okay,
You can check
okay.
once
Thank you, ma'am.
directly in portal.
Okay,
Yeah.
okay. Thank you, ma'am.
Yeah. Thank you. Anything else anyone want to ask about lecture or in general? Maybe we will wind up today's session with an example with the last question. The correct match for the intermediates given in column P with the reactions given in column Q is, so there are four reactants given here, this intermediates, and four options are here on this side: Fitzner-Moffat oxidation, Wills-Meyer-Heck reaction, Ritter reaction, and Swan oxidation. So which will be the correct answer? Answer is already here. So try to get the mechanism of each of this reaction. So here the correct answer is option 4. That is, first one is, we know it is 1 oxidation intermediate. Second one is Wilsmer-Hack reaction intermediate. Third one is Fitzner-Moffat oxidation intermediate. And last one is Ritter reaction intermediate. Now we have already seen the mechanism for this Fitzner-Moffat oxidation as well as Swan oxidation reaction. So I am not going into the details of that. Just we will see what is the basic mechanism of Wilsmer-Hack reaction and Ritter reaction. Hi Kiran, actually today's meeting is already done. Session finished almost.
Yes, ma'am, but the timing was, ma'am, till 5 p.m. to 7 p.m. So,
Yeah, so today's
was
the first session. So whatever questions I have come up with, we have finished the discussion early today. Five
oh,
seven
okay,
means
ma'am.
like five we will start. Mostly it will be around. It will finish around 6 to 6:30 maximum.
Okay, ma'am. I was not doing. Actually, I was busy with something else, so I was late
It's
for
okay.
that.
You will get the recording of this today's session and today's slides. Every session slide and recordings you will get in that NPTEL portal. Course portal, you can access all the recordings as well.
Oh, okay, ma'am.
So if you cannot join on time, it's okay. You can access it later also, whenever you'll get time.
Sure, ma'am.
Yeah.
So, ma'am, then I should leave now. The
Yeah. So
meeting
you
has.
are PhD or masters?
Ma'am, I'm master's student and pursuing MSc chemistry.
Okay. Where you're from?
I'm from OP Jindal University, Raigad, Chhattisgarh.
Okay. Okay. So in this session, I have just discussed that week zero assignment questions and just week one lecture contents. Then some people ask some questions regarding that. That's it. That was about today's session. Next session onwards, we'll come up with more problems, and maybe more time we can interact then.
Oh, okay, ma'am. Sure, ma'am.
Yeah. Then see you in the next session then.
Okay, ma'am. Thank you, ma'am.
Yeah. Bye bye.
Bye now.
So this is the mechanism of Wilsmere hack reaction. So what is happening? Firstly, this DMF will attack over this phosphorus center. This nitrogen lone pair will come over here, and this will attack over this phosphorus to form this intermediate. Then Cl minus will attack over this imine carbon, stabilizing the positive charge on nitrogen to form this intermediate. And then nitrogen lone pair will again come back, and this will leave to form this Wilsmere hack reagent. So this is the intermediate for this Wilsmere hack reaction, and it is basically used for the formylation. Now the next reaction is Ritter reaction, which involves nitrilium ion as the intermediate. So here what is happening? This alcohol will get protonated first, and then water molecule will leave to form this carbocation. Then to that this nitrogen lone pair will attack and form this nitrilium ion. So that is the reactive intermediate for Ritter reaction. So that's all about today's session. So in today's session basically we have seen how certain reactions, like combination of reagents, are used for the oxidation, like sulfur based oxidation, how different type of combination of reagents can give the same product but goes through almost similar mechanism. And then we have seen several problems related to oxidation and in general organic chemistry. So I hope this section was helpful for you. If you have any doubts regarding any of the lecture contents, assignment questions, or today's lecture content about the problems which we are discussing, feel free to ask. So see you in the next lecture session, which will be on the next Saturday, 5 o'clock. So thank you for joining and thank you for listening. Thank you.